me check.
I just turned it on.
Oh, okay.
We have another 30 seconds or so.
Let me check pronunciation.
Testing.
Okay, I think we're ready. And lastly, we have a set of lectures from Zohreh Davoudi from Maryland. She's going to be talking about quantum computing for quantum field theories and tell us what this picture is all about. So thank you.
All right, thank you very much. So I have not been in TASI as a student. I switched away too quickly from particle physics, but I remain close enough to the field of particle physics to be invited as a lecturer, so I'm happy about that. And I'm asked to talk about some sort of new developments in the field of high-energy physics, which is regarding the applications of quantum simulation and quantum computing in this field. So obviously, I'm not going to be able to cover everything. It's actually a pretty expansive and rapidly growing field. But I'm going to focus on something that is probably more suitable for a school like this. All particle theorists here, I don't have to explain too much about what the quantum field theory is. And I can just get to the heart of how we can approach simulating quantum field theories using these new technologies. So that's going to be the focus of the talk. So let me tell you a little bit about the structure of these lectures before I start. It's not going to be just slide presentations, but I'm going to start with a few nice pictures so that I can sort of increase your appetite for this field and say a few words about what the motivation is to consider this new technology in our field. I will then switch over to the Blackboard because the first lecture is going to be heavy on setting up the formalism for how do we quantum compute quantum field theories. We have to first understand what are the theoretical framework requirements for doing that. And that's essentially a Hamiltonian formulation of quantum field theories, and in particular, lattice gauge theories. So I'm going to spend sort of the first lecture to set up that problem for you so that at least we have very concrete models and frameworks to work with in the second lecture. The second lecture is going to be more focused on some basics and then specifics of algorithmic developments for this program. Once we have the theoretical framework, we can start asking the question of how do I map this theoretical framework to the language of quantum hardware. So that's going to be primarily the second lecture. The third lecture is more algorithmic developments, but also getting closer to the physics that we are interested in. So I'm going to give you an example of an end-to-end algorithm for simulating a collision process in high-energy physics. I mean, that's obviously our dream, to be able to, from first principle, simulate events that we see in collider physics and be able to interpret them directly from the standard model and hopefully learn something about beyond the standard model. So how can we actually set up that problem, write algorithms, and eventually compute them using quantum computers? That's sort of the goal. And towards the end of the lecture, number 3, if there is time, I'll give you a few examples of the kind of progress that's been happening over the past few years in terms of approaching various different physics questions and observables using the language of quantum computers. And we'll give you a few examples of the actual implementations on the quantum hardware, which is possible today, even though not at the scale that we would like to eventually achieve. But that's a stepping stone. Okay? So let's go through a few slides, which I would call pre-lecture. This is really sort of to set the context and tell you why we care about quantum simulation in particle nuclear physics. So this is really sort of a nice picture that would summarize what we are after. Okay? So we are particle physicists in this room. Our favorite model is a standard model, even though it has some deficiencies, but at least we know that this is the model that would describe the visible sector of the universe and 3 of the 4 fundamental forces in nature. still, despite the fact that we know this elegant theoretical framework, we have a lot of difficulties connecting this framework to complexities in the universe, right? So what kind of complexities we're talking about? We would like to understand how matter evolves, for example, in early universe, right? Can we actually have a first principle description of the evolution of matter and how it thermalizes and equilibrates based on the standard model? Obviously, it's a very hard dynamical problem. In the same way, we would like to understand and describe collision processes in experiment starting from the standard model. I mean, we talked about sort of experimental data today. You learned from Ben about the kind of data and how we can match them to the models. This is essentially a very hard problem, and a lot of these models and event generators that we have don't necessarily put in the standard model input for all aspects of the program, because there are some non-perturbative and complex aspects of the standard model that we can't just put in these sort of programs. Essentially, at the heart of it is that doing real-time dynamics, starting from these fundamental fields of the standard model, is pretty hard, okay? So can we describe these using a different sort of computational strategy? Also, I come from the field of theoretical nuclear physics. There are other questions that we care about. What are the phases of matter? For example, the interior of a neutron star that forms sort of one of the densest objects out there in the universe. Are we expecting exotic phases of matter? And then can we actually describe, for example, the merger of these neutron stars and predict gravitational waves by the knowledge or accurate knowledge of the nuclear physics of these environments? Again, these are very difficult questions. We've made progress in accessing various aspects of this physics using classical computers, obviously. And what is important to know is that there's a lot to be done. These are very hard problems. And that's why you think that quantum computing and quantum simulation might provide a new sort of computational and simulation framework to approach these problems. How do they work? Well, they use the principle of quantum mechanics, quantum superposition, and quantum entanglement, which is by itself a very interesting, deep, sort of conceptual aspect of these theories. The quantum entanglement. Can we actually learn something about the entanglement, the structure of these quantum field theories of a standard model, just because now we have this new technology to think about sort of more quantum mechanical properties of these models and these quantum correlations? That's something that we also hope to learn from this program eventually, okay? So that's really the roadmap for us. And let's just focus on this collision process, because I promised you that in lecture number 3, I'm going to teach you how to set up a collision process on a quantum computer, right? So this is sort of one of the ultimate goals. So why do we think that collision process is one of those sort of applications of quantum computers? Can we just classically simulate the scattering process? Well, it turned out that we can. In fact, using the method of lattice gauge theory that you've already heard of from lectures by Fiala Shanahan, how to sort of set up a classical computation of lattice gauge theories and really sort of access various set of physics observables that we're interested in nuclear high energy physics. The scattering processes is one of them, in fact. Despite the fact that the scattering process is a real-time dynamical process, we have a few tricks that will allow us to actually access scattering cross-sections using classical computing of lattice gauge theory. So what's the catch? Well, the catch is that we are able to do these processes just as low energies, okay? So what does low energies mean? It means that we're dealing with only a few particles, and we can only generate a few particles in the final state, okay? These are still very important processes. For example, for low-energy nuclear physics, there are processes like proton-proton fusion that occurs in the sun and produces energy, or processes like neutrino-less double beta decay that we're searching for in sort of neutrino-less double beta decay experiments out there, right? These are low-energy processes, and in the end of the day, they involve sort of a few particles, at least at the sort of fundamental level, And these are the kind of processes that we can actually start from the standard model and compute them. And this is something that we could not do 10 years ago or even 5 years ago. We are really making a lot of progress in being able to access the kind of physics observables that we could not even imagine a few years back. So this is already really good progress. And these are kind of a couple of examples from my work in this area. But this is sort of something that is happening. So I'm telling you this so that you keep in mind that classical computers are very powerful, and for the time being, they're going to help us to do a lot in nuclear and particle physics. So we shouldn't just like leave them at that. Okay, but as I said, we're interested in high energies, right? You're a particle physicist, your work is all about high energies because you want to produce new particles, detect new interactions, therefore you go to higher energies. Well, then it becomes very difficult. It becomes difficult because there are mainly two issues that we have to deal with here. The first issue is that making complicated states for these high energy scattering processes is pretty hard. Making very high energy protons or heavy ions for these heavy ion collision experiments is very difficult using classical computers. I'll tell you why in a moment, okay? And the second issue is that the computations that Fiala set up and the lattice gauge theory program is pursuing are, have kind of an imaginary time nature to them. We weak rotate to Euclidean spacetime to be able to do Monte Carlo sampling. And that's been very powerful, but in the end of the day, that would limit us to computations that are imaginary time in nature. So what if you're interested in a property or a process that is intrinsically real time, like these high energy processes, okay? So let me tell you a little bit more about why there are issues with, for example, making complicated states, starting from the standard model of particle physics, using Monte Carlo sampling techniques. Well, let's say that you want to build an atomic nucleus in your classical computer, starting from the quark and gluon degrees of freedom, okay? Atomic nucleus could be anything, could be germanium that you use in your dark matter detection experiments or in neutrino star beta decay detections. What's the problem? Well, the problem is that the complexity of these atomic nuclei would grow factorially with the number of quarks. Because remember, we have to build these objects out of the quark degrees of freedom. If you do a little bit of computation, you see that the numbers that you get are astronomically large. And these kind of computations won't fit into our classical computers at the moment. So we're kind of limited to a few body systems, like nuclei at the moment, okay? There's another problem, which is also exponentially bad, and that's the fact that when we look at these correlation functions of various states, nucleons, nuclei, they decline exponentially fast as a function of Euclidean time. And we're interested in the dependence of these correlation functions as a function of Euclidean time because they would tell us something about the energies of these states, right? So we would like to, for example, compute the ground state energies of these objects to start with. And resolving the signal out of the noise becomes exponentially bad, and it becomes exponentially bad with the number of atomic, with the atomic number, with the number of nucleons in your nucleus. There's another problem that is also pretty bad, and that's the fact that as you make these nuclei larger and larger, their excitation gaps become smaller and smaller, okay? So for example, simplest example, a deuteron, which is the lightest nucleus out there. It's a proton and neutron that are bound together. Their mass is about 2 GeV. And the binding energy of this object is almost like 2 MeV. So we're talking about orders of magnitude difference between sort of the energy scales that we care about in this problem. You really want to resolve the fact that these are bound objects. How do you resolve that signal from the noise? And now imagine that instead of the deuteron, you have something as complicated as a radon or some other atomic nuclei that are picked in this plot, then you really are in trouble. You need a lot of statistics to be able to resolve the signal for these large objects. Yes?
So if the complexity of, let's say, the proton is a bottleneck, would you be able to simulate just a parton level cross-section and say that there's a PDF times the hard scattering and just simulate that?
Yes. So that's not something that I'm going to talk about. Oh, yes. So can we actually simulate a parton structure function for the proton and then sort of fold it with sort of essentially separate the perturbative and non-perturbative aspect of the problem and approach the problem that way? Yes, absolutely. This is how things have been working so far. And lattice QCD has been really starting to provide such a structure function input into these processes. But in the end of the day, this is not sort of the first principle approach to the problem, right? We really want to sort of have everything at the level of the standard model and test some of these assumptions about factorizations and so on, right? All right, and I told you that there was a second issue, and that was the fact that we're pretty much limited to do imaginary time computations. What about real time? For example, can we look for non-equilibrium physics of a standard model, how matter evolves after heavy ion collisions, how it thermalizes, equilibrated, hadronizes? These are very important questions, and some of the sort of quantities that you define in this program are very hard to compute classically, like fragmentation functions and so on. So it would be really nice to be able to compute these objects, again, directly from the standard model, and particularly from the theory of a strong force. In principle, a wealth of observable that depend on Minkowski time in their definition. For example, the response functions, transport properties, structure functions. These are really sort of real-time, Minkowski time type of observables. And while we know a few tricks to get to some of these observables, in general, they are not accessible, okay, using our technique. So why that's the case? Well, because we do path integral, quantum Monte Carlo sampling of the path integral of QCD. And remember, if we go to Euclidean space-time, then we can get rid of this factor of I from our weight function. And then we end up with a real positive definite weight, which we can do Monte Carlo sampling with. If we don't do that, and we stay in real time, Minkowski time, then we have to deal with this highly oscillatory function. It's almost hopeless, because there is a severe sign problem that we have to battle. For these kind of real-time problems, Hamiltonian evolution turned out to be a more natural path, okay? So if you give me the Hamiltonian of the standard model, then you can apply this time evolution operator to your state, and then find out what the final state is as a function of time. This is very natural. Unfortunately, the problem is that the Hilbert space of the theories we're talking about here is huge, right? So there is no way that we can fit it into classical computers. And this is why we've been pretty limited in applying Hamiltonian simulation techniques to lattice gauge theories. Rather, we've kind of tried to stay in the realm of sort of action-based, path integral-based approach, because at least there, for certain problems, we can do Monte Carlo, okay? So this is really sort of the outline of why we care about bringing new ideas and new technologies into this field, because we're interested in first principle reliable computations based in the fundamental theory of the standard model, and maybe your favorite beyond the standard model. If you have predictions for your beyond the standard model theory, and you want to know how, sort of in terms of the real time, your theory behaves and so on, again, you need to apply the techniques that I'm going to talk about. So they're pretty general, okay? And then eventually, hopefully, we learn something also about the entanglement structure of these theories, and maybe we learn something more that we didn't know so far about at a more fundamental level about these theories. All right, so this is the outline of the lecture that is going to happen on the board after this point, just so that you can see the outline, and I would just skip putting the outline on the board. We're going to talk about the difference between Hamiltonian and Lagrangian formulation of lattice gauge theories a bit more. I kind of alluded to what the differences are, but let me say that a bit more, why these are like different strategies to simulating gauge theories. Number two, I'm going to talk about at least one Hamiltonian formulation of gauge theories that happen to be very useful in setting up problems for quantum simulation. This is by Koget and Susskind. There are other formulations as well, but we don't have time to go over all of them, but I'll tell you what are the sort of the differences between the different formulations very quickly towards the end of this lecture. So I will tell you how in this particular formulation we can think about states, Hilbert space, Hamiltonian, the action of Hamiltonian on the states. These are very relevant questions when you think about quantum computing, right? So we have to know all that. And then, as I said, I'll briefly tell you why there are a variety of formulations now that it comes to a Hamiltonian framework of gauge theories. And then finally, I'll tell you sort of a brief review of sort of what are the classical Hamiltonian simulations that are out there and why they are limited. So that's why we need a quantum computing method to do a Hamiltonian simulation of gauge theories. Okay? Any questions so far? Yes?
Lattice with these techniques could be able to determine the critical point of if there is a critical point?
Very good question. So the question is whether using these methods we can eventually learn whether there is a critical point in, I'm assuming, QCD phase diagram. Yes, exactly. I mean, this is like one of those holy grails of the field. And again, I kind of mentioned the atomic nuclei. The reason these are hard, at the heart of it is that these are finite density systems. Any finite density system is hard for us because it either brings a signal to noise problem that I mentioned or a sign problem. It turned out that if you introduce a fermionic density into your action, even if you rotate to the Euclidean time, you're still stuck with a complex action because of that. So this is a fermionic sign problem. So that's why we haven't been able to actually do much in terms of exploring all regions of the phase diagram of matter described by QCD. But yes, the hope is that these methods can circumvent that. And in fact, they can, because there is absolutely no difference between a zero density or finite density Hamiltonian when it comes to sort of the technology to compute them. So that's the beauty of that. Very good. All right, so at this point, I'm going to switch to the board. So all right, so let's first talk about Hamiltonian versus Lagrangian formulations of quantum field theories. Okay? Is it
the size in the back?
good enough size?
Okay.
Okay, perfect. All right, so let's on one side have, let's just start from this side and say this is Lagrangian, and this is Hamiltonian. I'm going to make a table to show a few properties and how these two formulations differ in terms of those properties. Okay? So what are the degrees of freedom well, in Lagrangian, I mean, if you start a quantum field theory course, usually are given sort of a Lagrangian to start with. In the Lagrangian, let's think about the scalar field theory for the moment, but of course, it applies to gauge theories and other quantum field theories as well. It's just easier to think about these fields. So the degrees of freedom are a bunch of fields, and obviously derivative of those fields. Okay? In the Hamiltonian, though, if you remember, then we deal with a bunch of operators, which are the fields, but also the conjugate variable of those fields. Okay? Now, let's say the starting point, so I just mentioned, in this case, it's just a Lagrangian that is a functional of phi and d mu phi. But on this side, we define sort of a Hamiltonian operator, which is a function of phi operator and pi operator. So already in this picture, I'm thinking about functions, and I can do analytical things with these functions, derivatives, integrals, and so on. As usual, on this side, I'm thinking about sort of a more quantum mechanical operator basis for these things. When I have a set of basis vectors, and I apply by these operators on those basis vectors. Those are kind of the two equivalent approaches to the same problem, okay? Let's see, what else? So what about expectation values? Okay, so on this side, the expectation value is obviously some path integral. If you remember, just the d phi of some operator O. It's just, and O is a function of phi's and d mu phi's, and so on. And then you have e to the minus s, it's a function of phi and d mu phi. In principle, this is e to the is, but as I say, the signature of a space-time for computational purposes is set to be Euclidean often. And therefore, this would change e to the minus s Euclidean action. Okay? And this would give you the expectation value, right? On this side, though, it's pretty simple. You have expectation of operator O is simply the state O state. So you have to tell me what the state you're interested in measuring the expectation value of O with, and then you just have this simple definition, where this is now operator O, acting on those states. Okay? Which,
I have a question.
yes.
In this one, what if the operator O has observables at different times? Don't we need to
Very good. That would be the next. Just bear with me. Yes, I'll get to that. Okay. So one thing that this brings is I kind of assume there are states and therefore a Hilbert space. Okay. So what about a Hilbert space? Well, I mean, obviously there is a Hilbert space here, but it turned out that for most practical purposes, we don't really care about it. And in fact, we can't even access it, because if you're in Euclidean space, what you're doing is like you're damping all the excitations, high energy excitations. You're like very sensitive to low energy excitations because of the action that you've chosen, this weight, and therefore we don't actually worry about Hilbert spaces, really, okay? So not relevant in a sense, which is kind of interesting. On this side, though, if I have an operator, I have to define what that operator acts on. So I have to define a Hilbert space, okay? So very relevant. So let me use this. And in fact, the way that we can build these basis states, maybe you can start with your Hamiltonian operator, and you act by that Hamiltonian operator in some sort of vacuum multiple times. And that would give you sort of all the basis states for your theory. Okay? And where vacuum means that you have empty space. You don't have any excitations in the Hilbert space of these operators. And I'll get to all of that through the examples. Okay? So if it doesn't really make sense, just bear with me. I'll give very explicit examples. I just want to say that there are ways to actually then build this Hilbert space. Yes?
So if you just take the vacuum and operate on the Hamiltonian to the power, and wouldn't that just give back the vacuum times its energy each time?
No. So when you have like empty space, this is not the vacuum of the Hamiltonian. It just means that it is when you have no excitations in the field. And now you can imagine your Hamiltonian is some, so let me get to that question when I talk about this explicit Hamiltonian in lattice gauge theories, okay? This is just, it is not the, sort of the ground state of this Hamiltonian. This is a state that has nothing in it, and then you can create a bunch of excitations in this state by acting by some sort of creation annihilation operators.
The Hamiltonian will always have phi in pairs of like phi dagger phi, so it will like annihilate whatever it creates.
So let's say these are just functions, some sort of creation operators of the fields, b's of the phis. Okay, I'll get to that more explicitly. Okay.
Did you want to have a signature space-time entry in your Hamiltonian?
Oh yes, did I miss that? Yes. Minkowski. Okay, you can do imaginary time evolution with a Hamiltonian framework, but in order to define a Hamiltonian to start with, you have to kind of have the notion of this continuous parameter that would evolve your states, right? So we kind of need that notion of Minkowski time to be able to define a Hamiltonian, okay? And then we can act by sort of make functions of those Hamiltonian to do different things. But really at the heart of this Hamiltonian framework is a Minkowski time, okay? So what else? We can do expectation values. Can we do dynamics? So dynamical.
When you write that low on the board, can you lift the board up a little so it's more visible from the back?
Sure. Okay. So what about observables or dynamical observables? As I said, this is very hard because we're dealing with Euclidean time, right? So very hard, so we can do limited things like low energy scattering, even some of these Parton distribution functions and so on. We can still use certain tricks to be able to kind of recover them in certain limits. I'm not going to talk about that. But as I said, it's non-trivial. And it doesn't always work. But on this side, this is pretty simple because there's nothing different here if the operator was time dependent. What you would do is to write this in terms of the Heisenberg picture. Operator at 0, e to the minus iht, and act by psi. So if you know how to implement a time evolution operator, then you can also implement the time-dependent expectation values. Okay? And I think that's all the entries that I want to put in this table for the moment. Let me just check I didn't miss anything. Maybe I'll add two more entries. I could just say it. What about computational methods? As I said, it's very common to apply Monte Carlo techniques here. Okay, because we have a well-defined weight, at least for most problems. On the other side, we could do things like exact diagonalization, which means that you give me the Hamiltonian, I find a way to diagonalize it, which means that I will find eigenstates and eigenvalues of that object. And then if I know those, then I can simply do the time evolution operator. It's just like sort of a diagonal operator. And it's pretty simple. Obviously, the caveat is that diagonalizing a large matrix is exponentially hard, right? Because exponentially in the size of the system itself, because the Hamiltonian has the size of the full Hilbert space, okay? So this is not very promising classically, right? There are other methods called tensor networks. For those of you that have heard of things like DMRG and other tricks that people, for example, in the condensed matter context, apply to Hamiltonian problems, this is like very similar in the same way. I'm not going to talk about this method either. It's one of those methods that is very powerful for 1 plus 1 dimensional problems, but unfortunately it's very difficult to make it work for 2 plus 1 dimensional problems, and then eventually for higher dimensional problems. And one of the other issues with this method is that it relies on the fact that your state has very small or bounded entanglement associated with it. It's a highly entangled state, and entanglement actually grows as a function of time. For the kind of problems that we're interested in, high energy scattering, then this ceases to apply. Okay, so again, so these are the classical methods. And as I said, they're pretty limited. And obviously, in these lectures, we want to motivate the fact that we can actually do quantum computing within the Hamiltonian framework. And we're going to see how it works. Can you do quantum computing here? What do you think? Meaning that I have a functional integral over there, and I would turn it into a quantum algorithm. Is there a problem with that? Say it out loud. It is not unitary, but we know tricks to how to turn a non-unitary operator to a unitary operator. So in fact, there is no roadblock in applying a path integral formulation of any theories in a quantum computer. And I can point you to at least one paper that sets up the problem and shows you how you can actually implement a path integral formulation of a harmonic oscillator on a quantum computer. But it's not very natural, okay? Because you're not dealing with the unitary operations like this, okay? So the problem is not really set up in a language of quantum computing. But any operation that you can do classically, you can also do quantum mechanically, okay? You can actually come up with quantum algorithms to perform classical tasks. But this is not the best use of the quantum computers. We have to kind of find the natural language for these computers. And it turned out that Hamiltonian is most natural. Okay? Any questions? Yes?
Can you talk a little more about what kind of observables are accessible through Euclidean Lagrangian formalism?
You have to bear with me for the entire 3 lectures. And not for the Euclidean, for the Hamiltonian. For Euclidean, let me just give you a few examples, and then we can move on. For the Hamiltonian formulation, the quantum computing side, I'm going to give you a lot of examples. But like for the Euclidean one, it's a very good question. The question is what kind of observables we can have access to using Euclidean Monte Carlo methods. And essentially, any observable that can be defined sort of in a static way, meaning that these are special correlation functions, non-temporal correlation functions we could have access to. Even if they are like non-local correlations functions, we can have access to those. Because in order to define those correlation functions, we don't need to define the signature of a space-time. Okay? Once we have to think about time, then it gets more complicated. So what are a few examples where you can get observables out of static or non-temporal correlation functions? Energies, like the mass of particles or the energies. There's no distinction between the energy eigenvalues in Euclidean and Minkowski spacetime. You can get access to these from a Euclidean correlation functions, but you can also get access to those from the Minkowski correlation functions. Things like form factors. again, you have a local current, like electromagnetic current, and then you're interested in knowing what the expectation value of that electromagnetic current is inside your proton or whatever state you're interested in. You can actually do that. The zero momentum limits of these form factors, which are a bunch of charges like axial charge, electromagnetic charge, you name it, tensor charge, a scalar charge of nuclei, which are very important for a lot of these experiments. You can have access to these as well. I mentioned low energy scattering amplitudes. And by virtue of this, we can also study resonances. Which are states that are searched for in a lot of spectroscopy experiments out there, okay? And so on and so forth. So there are a bunch of observables that we can compute. And as I said, anything that can be defined in a static way is accessible. Some of the things that cannot be defined in a static way, they are still accessible. I mentioned parton distribution functions. There are even tricks for getting things like transport coefficients. But again, they require solving very hard inverse problems. So the progress is being made, but we still don't have precise computations of those kind of observables. So quite a lot, but it's still kind of in terms of general real-time observables, this is where our hope is. Okay? Yes?
I think we are saying that the Hamiltonian is constant, right? Or this expression, I think that would.
What do you mean by constant? You mean in time?
Yeah, it's literally.
For standard model theories, they are time independent. But in terms of the algorithms that we develop, no, there is no restriction in terms of whether the Hamiltonian should be time dependent or independent. There are methods that will allow you to implement a Dyson series expansion of the Hamiltonian, the time dependent evolution operator. But for the sake of these lectures, we're going to assume that they're constant in time. Good. Other questions? Great. So let me see. We'll start new board. Okay, so topic number 2, as I said, I'm going to give you one Hamiltonian formulation. Of lattice gauge theories by Koget and Susskind. And that means that I'm going to talk about the following. I'm going to talk about degrees of freedom, Hilbert space, action of operators on basis states, and then eventually Hamiltonian itself. Okay? So that's the plan. And I'm going to give you at least 2 examples so you can see how it works for an abelian theory and you can see how it works for a non-abelian theory. Okay? So let's start from the simple case, an abelian theory. I'm going to start very simple, just 1 + 1 dimension. And I will tell you what changes if you go to higher dimensions. Okay? So let's talk about 1 + 1 dimensional U1 lattice gauge theory coupled to fermions. And I'm going to assume just one type of fermions, not multiple flavors, just one type. Let's just start simple, okay? All right, so let's draw some lattice sites. I'm going to start with a physical site. I'm going to call this physical site. And this is a physical site, and there are a bunch of other sites on either end of this lattice. Now, do you remember how many components of a fermion exist at every single site for a 1 + 1 dimensional Dirac theory? What's the size of your spinor? Okay, so you're saying that you have a 2-component field. Very good. Okay, so if you remember in 1 + 1 dimension and then 2 + 1 dimension, you can describe your Dirac fermions by a 2-component field. And then in 3 + 1 and then 4 + 1, you can use a 4-dimensional spinor to describe your Dirac fermions and so on. Okay, so here we're not dealing with a 4-component thing as you usually do in a standard model. It's going to be just like 2-component field. This is not very convenient. It is more convenient to have just one type of fermion or one single component fermion at each site. And that's why Kogan and Susskind suggested that we stagger these sites. So instead of one physical site, I'm going to end up with 2 staggered sites. That means that you actually separate out the upper and lower components of your fermions, put the upper component here, the lower component here, and you call them separate fermions, okay? Single component fermions. So essentially then you end up with a psi at x, psi at x + 1. How do you know that this was connected to upper component and this was connected to the lower component of the field? The fact that I would call these even sites and I would call these odd sites. So there is kind of a difference between even sites and odd sites. It's not going to show up at this level, but it's going to show up at the level of the Hamiltonian. They actually have different mass terms. Okay, so just bear with me for the moment. These 2 fields contribute differently to the energy of the system because they're kind of separated from that 2-component Dirac field. Yeah?
Are you going with the convention that then the gauge field, because it should live at the connector between fermion sites, would just live at the original physical?
Very good. So you do this at the cost of introducing twice the number of gauge links. And in fact, if you go through the derivation of the staggered fermions from the original Kogan and Susskind papers, you see that that's totally valid. Okay? You recover back the continuum theory, even though if you had just the gauge link in between these sites, now because this is now separated to 2 sites, you end up having an additional u in between them. And then you still have your u's on these ends. Okay? So that's no problem. All right, so let's talk about the nature of these objects. Well, as I said now, these are single component fermions. This is very convenient because if I have a single component fermion, it looks like a non-relativistic fermions, and I can then map it to qubits because qubits can either be 0 or 1, and therefore I have like 2 possibilities for the eigenstates here as well. And I'll get to that step later, but if you're just asking why I did this splitting of the components, this is essentially just kind of end up with the minimal number of sort of the possibilities or degrees of freedom at each of these lattice sites. Okay? And you may remember from Fiala's lectures that splitting or trying to put fermions on a lattice is a very hard problem. It introduces fermion doubling. You have to fix it. And then if in the way of fixing it, you may break other symmetries. And in order to restore those other symmetries, you may end up with more complicated lattice formulations of those fermions. All of that still holds in this picture because what I'm doing is just thinking about lattice fermions, nothing more. So you can apply those kind of lattice formulations here. I'm going to just apply the Kogan and Susskind formulation, not a bunch of other varieties, but in principle you could. Okay? All right, so what are the properties of these psi's? Well, psi x and psi dagger x are commuting, do not anti-commute, so x is 1. And similarly for psi at x plus 1, and every other fermionic field would then anti-commute. So all other anti-commutations are 0. The ones that are non-zero would look like this. So what does this mean? It means that I can now define the states like so. And then the action of psi, and let me just drop the x from this for the moment. There are like an x associated with all of these things. The action of psi on f is going to give you just f minus 1. And here, just to make sure I don't get extra, then you should put 0, f, and 0. And similarly, the action of psi dagger, and this basis states f, is going to give you 1 minus delta of f and 1, f plus 1. Okay? So that means that psi dagger psi is your number operator when acting on state f, is going to give you eigenvalues f times f, where f is simply either 0 or 1 because of this anti-commutation. And at every single lattice point, bring this down and this up. Okay. Successful attempt. Okay, so now we have a two-dimensional Hilbert space at every staggered site associated with fermions. Now I have to tell you what sits on the gauge links and define a Hilbert space associated with those gauge links, okay? So let's draw those staggered sites again. At site X, well, I'll do it in the middle of the board. Okay, so this is still site X. This is site X plus 1. And there is a gauge link that connects the two. And so in the continuum theory, you have an A mu field, right? But as we learned from lattice gauge theory lectures last week, hopefully, you can exponentiate this with the lattice spacing, the coupling, like so, and then define this gauge link operator that could sit in here. And I'm going to use the notation that the gauge link that starts from site X is going to be labeled by X. Okay? So now we're in 2-dimension, 1 plus 1 dimensions, and therefore there is an A0 component and there is an A1 component here. Now, well, it turned out that you can fix the gauge to what is called temporal gauge. And then redefine this to be just one parameter. And you can always go to temporal gauge in any dimension. Okay? So this is like one gauge fixing that we do. And that's fine. Okay? And as a result, I can just remove this mu. And I know that I'm dealing with a special component of the gauge links. I just like forget about this mu index here, because I just fixed the gauge. And why do I do that? It's always a good idea to fix the gauge as much as possible, because you don't really want to encode extra degrees of freedom that are just redundant, just computationally not efficient. Okay, so that's why I did this. All right, so we have the U field. And the same way that I have the psi and psi dagger, there were two anti-commuting, non-anti-commuting observables, I have to find conjugate variable pairs associated with this operator too, right? Associated with this degrees of freedom too. Any idea what the conjugate variable associated with the U field is? What else do you have in electromagnetism? What? Say it out loud. You mean E is electric field. Very good. Yes. So it turned out that there is an electric field associated with this link. And so why am I saying this is sort of the conjugate variable pair associated with this? The reason is the following. It turned out that E, and this is kind of the defining feature of a U1 theory. At this point, I'm just like defining the U1 theory, all right? So the defining feature is that E and then AGA give me something like 1 over I, okay? Which is very important. It says that it is E and A that are conjugate variable to each other, which means that I can turn this relation to E and U giving me E, U, okay? So strictly speaking, this is E and A that are conjugate variable to each other, but it's kind of the same to say that E and U also have a commutation that looks like this. So this is a defining feature of a U1 gauge theory. Okay, so now what does this mean, this commutation relation? It means that let's define now the Hilbert space. The Hilbert space that I'm going to define now is going to be in terms of electric field eigenvalues. So in the same way that in the discussion of a harmonic oscillator, you can go to the position space, or you can go to the momentum space, and then diagonalize one part of the Hamiltonian or the other, because these are conjugate variable pairs. In the same way, I can define to go to the basis states of the electric field or the basis states of the U field, because these are conjugate variable pairs. And I cannot simultaneously diagonalize in those bases. I have to like pick or the other. If I pick the E, then that means that I have electric field operator, and all of these are obviously operators, acting on this basis state is going to give me E, the content of this state, times E. So this is now an eigen state, an eigenvector of the E operator. What about the action of U in this basis? Well, we can read it off based on this commutation relation. Any guess? Exactly, translation by 1 unit because of this relation. And interestingly, the coefficient here is just 1. So this is not really the Hilbert space of a harmonic oscillator. Do you know what this algebra belongs to? It's also a very sort of known quantum mechanical system. Yes? Very good. So it's a quantum rotor. Looks very similar to harmonic oscillator, but not quite, because I don't get the square root functions of the occupation numbers here. It's kind of simpler. Okay? So this is like the Hilbert space. Now, how can we now explain or describe a generic state in the theory in terms of these basis states? What are these basis states? They're electric fields at every position x, and then there are F fermion numbers at position x. Well, obviously, I can just tensor product all these guys to get sort of a description of all the states that are possible in this basis. And I'm not claiming that these are eigen states of a Hamiltonian, because I haven't defined any Hamiltonian whatsoever. Okay, I'm just saying that you can span the Hilbert space of operators that have algebras like so, using these basis states. Okay? So let me go to this slide. So I'm going to draw these staggered sites again. Let's call this x, x minus 1, x plus 1, x plus 2, and so on. Okay? So as I said, you can just take, and there are a bunch of links in between them. And as I said, you can take the f operator at x minus 1, cross-producted with the e at x minus 1, with the Hilbert space over here, and then the Hilbert space over here, to get all the states for a lattice of n staggered sites, okay? So now the question is, are all these states physical in a U1 gauge theory? Well, it turned out it's not. Again, it's just sort of a defining feature of the theory. It goes back all the way to the Gauss's law in electrodynamics. All right, so in this form, all these states are not valid. Only the ones that correspond to the following constraint are valid. So let's talk about them. So let's define an operator that would call Gauss's law operator at position x. And this operator is defined as Ex minus Ex minus 1 minus an operator Q, where operator Q is defined as minus psi dagger x psi x plus 1 minus 1 to the x over 2, just by definition. And we will see that this is actually a charge or electric charge operator for this staggered theory. So now the physical Hilbert space is the one that gets annihilated by this operator at all points. Okay, so some important relation. And let me just finish this. And what this tells you is that at every single point, you have to check whether the flux of the electric field that goes out, sort of the net flux, so there is a flux that comes in, there's a flux that goes out. So the net flux, which is the difference between incoming and outgoing, would be balanced by the electric charge that is sitting at that site. This is exactly the statement of the Gauss's law in electrodynamics. And this is showing up in a lattice theory in 1 + 1 dimension. It's nothing more than that. What's the question?
Nothing. I was wondering about the last term.
The last term, we come back to it. This is why I said there is a difference between the upper component and lower component. We kind of call them psi, but we have to always remember that depending on whether they sit on the even or odd side, they have different properties. And this is like one example where that shows up. Okay, so all of these are at the moment pretty formal. Let me just work out an example to see how it works. Okay, any questions so far? Yes?
So in the anti-commutation relation, where you have anti-commutator psi of x, psi dagger of x, could it be written more generally as like embrace psi x, psi dagger y equals product or delta xy?
And so this is on the lattice, so there is no kind of delta function, the Dirac delta function. If you mean the Kronecker delta, yes, it could.
Okay.
Yes, exactly. So all of these are fermions, so whenever you pass them over each other, you have to get a negative sign. And one thing to notice is that you also have the commutation. The fermions at different sides, they also commute because they have nothing to do with each other. But the commutation of the fermions at the same side, that's non-trivial because of that non-trivial anti-commutation relation. Yes?
Oh, never mind. I think I actually.
Okay, good. So I think if I work out an example, so this side is also good for people. I suppose it's even better for this side of the room. Okay, so let's work out an example.
By the way, there's about 11 minutes left.
All right, sounds good. So let's work at an example. And this is an example of a two-side theory with periodic boundary conditions. And we want to answer the following questions. Number one, how many basis states are there? Number two, how many physical basis states are there? And we have to identify what they are. And number three, what is the total electric charge associated with them? Okay, so how many basis states? This is a two-side theory, okay? So it is periodic boundary condition, which means that if you have a link that connects these two, there has to be a link that connects back. Okay, that's the meaning of the periodic boundary condition. So we still have our site x and x plus 1. So let's just call this 0 and 1 because there are just two of them, and I'm going to index from 0. Okay? So then I have f at 0, f at 1, and I have E that originates from 0, so I would call this E0. And this is E that originates from 1, and I would call 1. So with this, how many basis states are there before applying the Gauss's law constraint? 4 for the fermions. Okay, so 2 to the 2, because there are two sides, and each of them could be either 0 or 1. What about the gauge links? In principle, infinity, right? So one thing that we should have noticed here is that this is the Hilbert space of a quantum rotor, and this E is integers. It can go from minus infinity to infinity. Well, this is expected. We're dealing with a continuous group, and a continuous group is, has infinite degrees of freedom, essentially. Whether you're in an electric basis where you have a discrete but unbounded spectrum, or if you're in this U basis, then you have a continuous but bounded Hilbert space, but it's still infinite degrees of freedom. It's nice to work with the E basis because everything is discrete in units of 1, but then I have to cut it off. So here, the answer would have been infinity, but for any computational reality, we have to really sort of put a bound on this. So then I would say, consider the case where electric field could be only between minus 1 and 1. So there are only 3 values, 0 or plus minus 1, which means that I have very low cutoff on the electric field basis. Okay? So in that case, then there are 3 possibilities here, 3 possibilities here, and you get 36. Okay? So I have to be a bit faster. So let's talk about the physical states. Obviously, all these possibilities for states, 36, they're not physical. We have to go through all of them and check at this side and this side whether the flux of the electric field is balanced by the charge. And I'm going to give you those states, and if you don't believe me, you can sit down and go through all the options or write a computer program that will give you those states. So what are those states? One of them is the following. Well, I'll write it, and I'll tell you why that's the case. So 0, I tell you what the notation is. So this is at site 0, and then 1. 0 at site 0. Let me check whether this is correct. So this is the electric field, and this is the F at site 0, and this is F, and this is E. Okay, so one way to test whether this is a physical state is to quickly go through the charge operator. So you write Q at position 0, and by definition, which is over there, is going to be minus psi dagger psi, which is minus 0, plus 1 minus minus 1 to the index 0 over 2. And this gives us 0. Yes?
Sorry, both of these are at site 0?
Oh, sorry, this is site 1. Thank you. Okay? So the charge at site 0 is this one. The charge at site 1, F is 1 because that's the psi dagger psi. So that's, we get minus 1 plus 1 minus minus 1 to the 1 over 2. And this is also 0. Okay? So the charge, use a different color. The charge of this state is equal to 0. The charge of this state is equal to 0. So now if I have a charge 0, that means that the flux of the electric field should not change because I have 0 charge, which hasn't changed because I go from 0 to 0 and back. So that's a physical state. So you can also guess what the other cases are, because I can have exactly the same fermion content, but I can have 1 over here, and then exactly the same fermion content, and then 1 here. And then number 3, I can have exactly the same fermion content, but minus 1 here, and exactly the same fermion content, and minus 1 here. Because I have also the option of not changing the electric field, like 1 and minus 1 and minus 1, because the charge is still 0. So these 3 options are also consistent with the Gauss's law. Yes?
What about if we have a circulating electric field, total electric field, does that allow?
Circulating, I mean, it is a circulating electric field, right? Because 0, 0 is kind of winding around. So you can interpret it that way, because it's periodic. Good? All right, so let me tell you about quickly the other 2 options. So then number 4 is going to be when the fermion content is changed, and we have to figure out what the electron content is. So then that would be 0 times the fermion content at 1. So now, because of this change, you can guess the Q is no longer 0. If you actually do that math, you get Q minus 1 here, and you get Q equal to plus 1 here. So I would then call this an electron and call this a positron. And now because I have a charge minus 1, so you have a charge that is equal to minus 1 here, you have an electric field that goes out, electric field comes in, so this guy should be less than this guy by minus 1. So one option is that this is 0, and this is minus 1. Another option is that this is 0, and this is 1. And that's it. So in terms of this one is minus 1, and this one is 0. And the number 5 is the same fermion content, but then it's going to be 0 times the same fermion content, and now 1. And it turned out these are all possibilities. So we had 36. If you wanted to encode all that Hilbert space in our quantum computers or qubits, we would have needed logarithm of 36 qubits. But now we only have 5. So we essentially need 3 qubits to encode this Hilbert space. So that's very important when it comes to gauge theory constructions. Okay? The last part of this question is, what is the total charge, electric charge in the system? Which means that just summing up the charge of 0 and 1 lattice sites. So for this guy, it's 0. For this guy, it's 0. For this guy, 0, 0, 0. Is this a surprise? Can you have non-zero charge with periodic boundary condition? So this is like a quiz question for you. Think about it. Think about why it is the case that you cannot have a non-zero charge with periodic boundary conditions. In fact, if you had an open boundary condition, then you could have different charges. Open boundary condition means that You have your lattice sites. You fix the electric field that comes in to some value, let's say 0 or epsilon naught. And then you let this last one to be open, whatever it needs to be to satisfy the Gauss's law at this point. So this is called an open boundary condition, sometimes fixed boundary condition, but that's called the periodic boundary condition. And they have very different physics, because as I said, you could have different charge sectors here, but here you just limit it to charge 0 sector. In the limits of infinite lattice size, they're supposed to recover the same physics, but for any finite lattice size, there are kind of different theories. So something to keep in mind. All right, any questions? So was this example clear? But I'm going through this example because I'm going to build quantum algorithms for simulating a theory like this. So it's very important that you understand the physics, the Hilbert space, and eventually the Hamiltonian, the action of Hamiltonian operators, all of that. So that's why I'm very sort of specific about this example. Okay? All right, so we don't have time anymore. I was hoping that I could at least tell you what the Hamiltonian is and leave some discussions of non-abelian theories for next time, but I guess, all right, sounds good. So we'll continue tomorrow, okay? All right, questions?
More question if we have one. Okay, we didn't hear any questions, so we can have some discussion after as usual. Otherwise, you're all invited back to Ben Knockman's public lecture.
Yes.
Ask a very
Yes,
basic question,
of course.
and I got lost a bit.
Yes.
So we said we are in 1 + 1 dimension, and we have 2-dimensional spinors, and then we do the staggered states. So I was expecting that, like, when we duplicate these states, we are considering like spin up and spin down, living on 2 different sides. But it seems that each side has 2 degrees of freedom. Like it can either be up or down. So what am I missing here?
No, so in 1 + 1 dimensional QED, you have electrons and positrons. Now, electrons could either exist or not exist, and positrons could either exist or not.